All right, everyone. Welcome back or welcome again. Now we have a great topic right now, AI applications in automotive security. And with us, we have Janahan, who is currently the Senior Director of Research and Development at Arctic Wolf Networks. And he's leading the AI and data science teams, as well as the security research and threat intelligence research teams and mandates there. He's going to give us an overview about how AI fits into this automotive security um, topic today. So, Janahan, thank you very much for being here. The stage is yours.
Okay, thank you very much, John. So, again, excuse the lighting that I have in my room. I kind of look dark because I have the lighting at the back and so forth, but excuse that. AI and its applications to the field of automotive security. So, I assume everyone can see my slide deck. So, first, let's look at let's look at where we stand today in in the automotive industry with respect to autonomous vehicles, connectivity, cybersecurity, and how AI is applied today. Okay. Now, as of today, as most of you might already know, the Society for Automotive Engineers International have defined 6 levels of driving automation, from 0 to 5. So there's level to level 5, where level 0 is no automation, and level 5 is full self-driving automation. So you pretty much don't need a driver. Today in the industry, we're mostly at publicly available level 2 vehicles. So level 2 vehicles where there's a combined function of automation, and the vehicle has multiple automation features, but the driver is still required to pay attention to the road. Now, there are some level 3 vehicles by some companies that are in the prototype stage, but they've not been released for general consumption and public use as of yet. Now, there are 3 main attack surfaces today in terms of cybersecurity for the automotive industry. There's the supply chain, the in-vehicle, and the cloud. So in cars today, you have in the actual cars, so in vehicles, you have today interconnected ECUs, electrical control units. You have radio frequency devices. You have Bluetooth, Wi-Fi. You have networks such as CANs, Ethernet, local internet network, and MOST as well. So MOST is media-oriented system transport, so the entertainment systems and so forth. And you also have a centralized control system. And as most of you would realize, the centralized control system there is the touchscreen system that has access to driver profile, navigation, temperature, lights and display settings, autopilot and driving preferences. The touchscreen also has access to Wi-Fi, Bluetooth, and radio frequency devices as well. Now, the driver profile includes steering wheel position, rear view mirrors, seat position, and lights. And there's a bunch of other there's a bunch of other information that's also stored in the driver profile. The reason why I was bringing up these specific items was the impact that could occur if the touchscreen system was compromised, right? So, and by the way, the driver profiles and all that are stored in the cloud as well. The centralized control system also controls the assist systems for safety. Now, these can be turned off if you don't need them, but you have in cars today, you have lane assist, collision avoid assist, and speed assist. Now, let's take a use case, right? So let's assume that your car is compromised while your car is compromised. Imagine while you're driving, if your seat position or your steering wheel position or rear view mirrors and so forth are basically changed while you're driving, right? There's a very dangerous effect to that. Similarly, imagine if you assume that your collision avoid assist, speed assist, and lane assist are turned on, but because of the compromise to the system, they've been turned off. These are basically attack vectors within the in-vehicle attack surface that can lead to some serious, some dangerous consequences. You also have, for example, your mobile app that lets you communicate with a car, and you can using the mobile app, you can also open the front or the rear of the trunk. Imagine if you can if the front or the rear of the trunk opens while you're driving, right? Then you have the autopilot system, the minimalistic autopilot system that we have today, where there's traffic aware cruise control automatic steering, navigation on autopilot, traffic light and stop sign control, automatic parking, and also summoning of the vehicle. So again, these basic systems, if compromised, can basically cause serious damage. The other thing with vehicles and the push towards more autonomous vehicles are that autonomous vehicles, as they get more autonomous vehicles, are based on the system of basically taking in information from sensors and then making decisions based on that, right? So sensors such as lidar, light detection, ranging and ranging radar, even sonar sometimes, and also multidimensional data and 3D scanning devices, computer vision, the cameras, and so forth, right? So the way autonomous cars work today is, and they would be working as such going forward as well. It's basically an input of data using those sensors, and then they use sensor fusion to basically make the best decisions based on the data that they receive. Sensor fusion meaning there are different types of sensor fusion, right? There's complementary, where one sensor sees a certain dimension, another sensor sees a different dimension, and they complement each other to make a decision. Then there's basically sensors that basically get the same information in different ways. And so if one sensor has information that's different from the other sensor, then obviously there's something that's happening, right? So the sensor might be off, or it might be a cybersecurity event in terms of sensor spoofing, basically giving, hacking the sensor and basically giving sensor spoof data, right? And so decisions are made from that respect. So as you can see, the in-vehicle attack surface is quite broad and will only increase with increasing intra-vehicle connectivity. So as cars get more advanced, their intra-vehicle connectivity, the connectivity that occurs within the connectivity and exchange of information that exists within the car increases, and also the centralization of control of that is also basically used. It's not distributed because it's basically an ease of use perspective, right? Now, from a user experience perspective, if you look at the touchscreen and so forth, while this brings amazing user experience through ease of control, it also brings ease of applying malicious activity. So remember, if it's easy for us, it becomes easy for bad actors who have our key. And this applies to all industries. The more the connectivity, the bigger the attack surface. Now, for the cloud attack surface, with regards to cars, today, software updates occur through the cloud. Driver profiles, as I stated before, are stored in the cloud. Native and third-party apps that the car uses that log data to the cloud, such as driver stats, charging stats, history of installed updates, information on when the car was online or asleep, visited addresses, and so forth, right? And then you also have the option of enabling data sharing even further, where information goes to your cloud for analytics. That also occurs today. So there also, if such information is compromised, you can get information to basically cause some serious damage. For example, if you look at the history of installed updates, and you're say a bad actor is able to look at the history of installed software updates, and then identify that a certain update, it's at a certain version, and that version has certain vulnerabilities that can be exploited to basically hack or compromise the car, then he basically gets in that way. So there are many attack vectors that you can use lines through as the connectivity, even through the cloud, occurs. And then last but not least, you have the supply chain attack surface. So vehicles have been moving from mechanical to basically, there were mechanical vehicles in the past. Now they're moving to more, and they got into electronic and so on, but now they're almost like moving computers, right? And there are a lot of hardware, firmware, and software components. So with regards to the supply chain, if there are any backdoors, Trojans, or even unintentional vulnerabilities, and what I mean by unintentional vulnerabilities is there's a lot of open source code that's used as well for software and so forth that that are used for cars. If the software has a vulnerability that no one is aware of, a 0 day whatsoever, and is discovered, then that could be used to compromise, and that also occurs from the supply chain attack surface. So as you can see, These three attack surfaces can be used to compromise a car and cause damage in quite a serious fashion today. So, how is AI applied today to secure the vehicles and ensure automotive security? So, I will focus mostly my talk on there are a number of ways to apply cybersecurity to these problems. I'm going to look at the AI applications with regards to that. So, for in-vehicle security, you have the list of networks, right? Your CAN, Ethernet, Bluetooth, Wi-Fi, the local interconnect network, and media-oriented system transport. The AI algorithm. So I'm going to talk about in today's current state, where we are today, how we apply today for the type of vehicles, level 2 vehicles, and the system, and where we are today with regards to that base. So today, the AI algorithms that are mainly used, especially for in-vehicle security, in terms of the network aspect, is basically anomaly detection for network usage. So for instance, the CAN network misusage. We use statistical learning and GANs, basically generative adversarial networks, for abnormal usage identification. We learn message rates. We use learning for message rates in the CAN bus for specific ECUs, so electrical control units, and then we find out abnormal message ID patterns and so forth. There's also usage of anomaly detection methods such as engrams for anomalous Bluetooth communication. Also, graph analysis and machine learning on graphs, so basically using graphical neural networks and community detection algorithms, are used to identify C2s, so command and controls, IP and domain fast flux, and DGAs, domain-generated algorithm-based domains. So these are currently used today from a network perspective to basically detect cybersecurity compromises from a network perspective. And this, of course, overlaps with a number of other industries. So, again, now talking about other industries and the automotive security industry, all industries, when it comes to cybersecurity, there's a lot of overlap, cross-pollination, and so forth. So, as you can see from networks themselves, the entire network infrastructure and so forth that started with telcos, critical infra, IT and OT systems, and SCADA and so forth. There's a lot of knowledge to be reused there. So today, these methods that I just mentioned for networks are used in those industries for phishing detection, C2s, lateral movement, remote code execution, remote access trojans, and so forth. So that's kind of a usage of how we use it in automotive security as well. Also, the IoT security industry uses behavioral modeling of IoT devices to identify anomalous behavior. You can pretty much claim that these vehicles are soon going to be IoT devices as well. Right now, from a cloud security perspective, as I said, native and third-party apps, they log data. So AI algorithms here what we use in the cloud today is again used by all industries that have the cloud that use the cloud in their ecosystem or the application of their solution. And the AI algorithms that are mainly used there are mainly used from on the WAF perspective. So the web access firewall that basically use ML-based techniques such as engram methods and deep learning-based methods like RNNs, so recurrent neural networks, LSTMs, long short-term memory networks, to inspect incoming requests for attack vectors such as structured query language injection, cross-site scripting attacks, web shell, and RCEs. So that's because the data that's there, the application of cloud security, there's a whole field and base there. Most of it is almost one for one today in terms of what we can use for cloud security for the automotive industry as well. On the supply chain security side, when these vehicles are developed today, there's both in-house and external software that's basically used, as well as hardware and so forth. But mostly on the software side, because that's where it's easy to basically put in backdoor trojans, and there's a lot of vulnerabilities, unintentional vulnerabilities that can occur, especially with open source software. Again, this is used across industry. What they usually do is they use they basically use static and dynamic analysis of the software artifacts, right? And mostly what they use, and from an AI perspective, CNNs, convolutional neural networks, and random forests are used basically there and it's applied to the binaries, to the actual software binaries, and also if you generate the PCAPs from dynamic analysis, you can apply it there as well. So random forests are applied to behavioral data. So from the perspective that features from system calls, file system interaction, registry analysis, and so forth can also be used to detect vulnerabilities. Then, of course, there is the field of AI-based fuzzing to basically fuzz data as inputs to the software and applications. So generative models such as autoencoder, decoder, and GANs for AI-based fuzzing to generate inputs are also used as test cases to identify vulnerabilities. And again, this overlaps with almost general software development and hardware development industries. Now, looking into the near future in terms of cutting edge and potential uses of AI for security for the near future state of the automotive industry. So near future, I'm talking, so in the near future, say we get to the stage of level 2 or 3 cars and somewhat increased connectivity. What is being worked on right now? So one of the things with regards to the cybersecurity industry, especially what AI is being used for, is basically to use AI to cross-check across multiple attack surfaces and multiple attack vectors. So, for instance, event correlation and contextualization is currently being worked on and used in a number of areas, and that is an area that we see it's going to be that could be used right now as well in the automotive industry. So basically, this is threat chaining across different surfaces. So probabilistic graph models such as Bayesian networks and Markov networks can be used here for event correlation and contextualization. Now, sorry, I just saw a chat. Are you guys seeing the slide that says threat chains, federated learning, and ontological reasoning? Okay. All right, just wanted to make sure. Yeah, so I think the previous 2 slides, this was the first slide. The second slide, I had the algorithms at the bottom, and this is the third slide. So that's where the confusion must have come across. Sorry about that. So as I was saying, event correlation and contextualization. What it's usually used for is today you can get, for instance, let me give you an example. A single malicious activity can manifest itself in 3 different dimensions across 3 different vectors. Okay, but it's the same malicious activity. And the way it manifests in 3 different dimensions, they might not be significant enough to basically, pique your interest. But if using AI, if you can do event correlation and contextualization and basically look at the context of each one of those events and correlate them with each other, and you can basically, you might come up with an actual the identification of an event that may be even in progress based on the sequence of events based on the threat chain or the kill chain, right? So that's an example of event correlation and contextualization that's used. And it is basically looking at a number of events to see correlation there and creating threat chains to give a better view and context of an attack that's going to be in progress. So threat chains across the 3 attacks, across information across the 3 attack surfaces is something that we see that could be used that could be used in the near future. Federated learning. So basically, with the increasing amounts of data that we see right now and that we will be seeing, the centralized orchestrator and edge computing and the concept of MEC, mobile edge computing, becomes more favorable, right? So federated learning basically is the learning is done basically at the client and the server, basically across areas. So here it would be where we stand today, cloud to vehicle only. But at least with regards to the increasing amounts of data, AI algorithms that are being used from a cybersecurity perspective can be used in that perspective of federated learning to help with identifying cybersecurity attacks and compromises. And then you have ontological reasoning and expert systems. So basically, deductive reasoning using description logic to make inferences. So this is a field that we see that can be used a lot in the automotive industry as well, with regards to where we're going, because it helps with the attack and defense ontologies for detection and response. So the advantage of ontologies is that it decouples business logic from runtime logic for making inferences. So let me give you just an off-the-cuff example of an ontology, right? Let's say we have the following facts and rules in a cyber ontology. If a process reaches out to a C2, a command and control, to download a malicious binary file and then runs it, it is classified as a downloader. Okay, so downloader is a subclass of malware. If something is a malware, then it can also register malicious registry keys and scan your network for other vulnerable machines. Now, let's say you detected an application that reached out to a command and control center, a C2, to download a malicious binary file and then ran it. Now, this could have been detected through rule-based and ML approaches, multiple ML models and all that, but it's used to detect. Then, based on the above rules in your ontology, you can make the following inferences. The inferences are: the application is a malware. The application can try to register malicious registry keys, so perhaps you should scan your registry for suspicious keys. And this application can scan other machines in your network, so you should inspect your network logs. So these are the inferences. So that's the advantage of ontologies, is that it decouples business logic from runtime logic for making inferences. Now let's go into the foreseeable future, into the long-term foreseeable future. So the long-term foreseeable future. So what I just spoke about was, I first spoke about AI algorithms that were being used today. Then I spoke about future AI cutting-edge algorithms that can be used in the context of today's infrastructure, vehicles, and so forth. In the near-term future. Now I'm talking about the actual long-term foreseeable future as we can see it today. Kind of the futuristic view. So the future is actually a fully connected future with level 5 fully autonomous vehicles. I mean, that's what everyone views, right? So here, for intra-vehicle connectivity, the connectivity within the vehicle will get more complex. The car itself will become an enterprise network in itself, pretty much, because there will be so much in there. Then from a network's perspective, and this is the big change that would occur, because now it's mostly communication with the cloud. From a network's perspective, you'll have V2V and V2I, so vehicle to vehicle and vehicle to infrastructure for inter-vehicle communication and vehicle to infrastructure communication. So, basically you'd have transfer of basic security messages through those infrastructure, right? Now, from a use case perspective, this kind of communication would, from a security perspective, the use cases of what needs to be avoided, basically, because all of this can happen, is collision. Like the cars, if it's an autonomous vehicle, it has to implement, by fully autonomous vehicle, it has to implement collision avoidance, turning, lane change, roadside service finders, merging, emergency braking, and then vehicle platooning as well. So vehicle platooning is like what happens for drones today, right? So drones, they platoon together to move in a certain streamlined form. So vehicle platooning is something that's being envisioned for the future, where there's a streamlined usage of highways. So cars can travel closely together. The platoons will decrease the distances between vehicles using electronic and possibly even mechanical coupling, right? And this capability would allow many vehicles to accelerate or brake simultaneously, right? And this system will also allow closer kind of headway between vehicles by eliminating the reaction distance that's required for human reaction, right? Because humans need to have a certain reaction time, because they can't. There's no view of all the cars and where they are and what's happening at the same time within a certain time period. While it's platooning, controlled by a central orchestrated system, or even inter-vehicle communication can control that. So vehicles will be able to be joined, leave platoons automatically, and so forth. So then you would have also communication with traffic information systems, right, and roadside units. You'll have information systems that give, for instance, road surface conditions. So, with certain surfaces, there are speeds and so forth. You'd also have navigation services, and on-the-road services and so forth that would be sending information, that would basically sending information to your vehicle and vice versa. Now, V2X, which is the vehicle to infrastructure, other vehicles, and so forth, involves the data view fusion of all the vehicle sensors. So unlike today, where the vehicle itself just fuses its own sensors, and sensor fusion occurs there. This would the V2X would basically allow sensor fusion across vehicles to give better information, analytics, and so forth, to basically help with both from a driving perspective and a security perspective. And then obviously you have your smart networks, edge computing, 5G, and so forth, right? So those are also part of this infrastructure, where there'll be network slicing enabled through software-defined networking. You'd have dedicated logical network slices to enable ultra-low latency and high reliability-based communications. So you'll be leveraging SDN and NFV. There will also be we can envision basically third-party applications partnering with telcos to rent real estate on the edge. That also can happen. And basically other vehicle-to-vehicle protocols are envisioned as well. So for instance, dedicated short-range communication, DSRC, wireless access in vehicular environments, WAVE, right? So these are vehicular ad hoc networks and these could be used to help with platooning, right? Now, and then you also have connected infra. So you have eye to eye, so infra to infra. So basically, for instance, electric vehicle charging infra integrated with microgrids, smart traffic lights, right, that collect traffic information that will help with analytics on the edge or in the cloud, right? And then you'd have cloud applications for vehicle, where you'd have, like I stated before, now that all the information is coming, is being used across vehicles and with the cloud, there could be dynamic traffic management for, adaptive traffic signal timing, right? So, today, traffic signals usually, they use a kind of rudimentary system to see if cars are, with regards to the number of cars in a certain road and all that. This could be more streamlined and helpful from a dynamic traffic management perspective. Right, and then you have dynamic rerouting. You'll have dynamic rerouting of traffic, smart parking. There are many applications. Now, with all these applications, the attack surface increases, tremendously. Okay, the biggest attack surfaces and attack vectors that can happen here are data manipulation attacks. I mean, that's the biggest, right? Because the usage of data to make decisions, both from a driving and a security perspective, data manipulation attacks is the biggest. Then you have, sinkhole attacks. Basically, for instance, when you're doing collaborative routing, if data is sinkholed, information is missed. And then you can have masquerade attacks as well. Attacks where a vehicle basically, call it vehicle identity theft, where an attacker obtains valid security credentials and then masquerades as another vehicle. And then you have, of course, sensor spoofing. Previously, we said internal sensor spoofing. Now it'd be external sensor spoofing in terms of sensor-based data that's communicated between vehicles. So a lot of attack surfaces, because the increase in connectivity and of course increase of connectivity infrastructure and movement of data in the futuristic view that we're moving towards. Now, with that, so what is the view of AI from a cybersecurity, from an automotive security perspective here? So this is, again, these are all concepts that are being researched right now, and basically what I'm talking about here is where it seems to be growing. So seems to be going, and kind of what makes sense in the near future. So do remember that if you look at a fully autonomous vehicle, okay, even today there's certain functions that are done to help with making sure the driving of the vehicle is safe and fine, right? So now move it over to a fully autonomous vehicle. In a fully autonomous vehicle, there is an AI, what I call an AI driver brain. An AI driver brain is pretty much the AI that's used to gather data, make decisions, and move the vehicle so that it's safe, it doesn't hit anything else, and so forth. Okay, based on data that it gets, communications with others, making best use of decisions on moving left, moving right, speed, all that other stuff. Now, there is a layer on top of that, which is, and that layer is kind of subsumed right now at where we are today, but we see that layer splitting up as a separate AI security type brain. So let me give an analogy to kind of explain the difference between an AI driver brain and the AI security brain. This is where the AI security brain and the application of security in this highly connected futuristic um, state will go. So, assuming that, let's say that there are two people in a car that's going. Okay, you have the driver and you have someone sitting next to him. The driver basically would look at his rear view mirror. He'll look at he'll see the road conditions. He'll see other cars, all that, and he will make the best decisions to drive his car in a safe fashion so that he doesn't hit other cars or there's no issues and all that. But his focus is on immediate driving, right? Now, intrinsically, that is in a sense cybersecurity too, to a certain, not cybersecurity, but security. It's security to a certain extent because it's on the aspect of safety. He has to be safe. For instance, if he does something stupid and doesn't take data properly from a certain sensor, from his own senses, and he moves to in a certain way, he could cause a crash and all that other stuff, right? So that is, let's view that as the AI driver brain, that person that's sitting in the car driving. Now you have another person sitting next to him. This person is not focused on immediate driving. This person is focused on looking and monitoring all what he's seeing as the car is being driven by the driver and the data that's coming in. So let's say the car is going and the driver sees something in the rearview mirror, sees it in the see stuff on the road, see some signs. Signs are like road size units and all that. He sees a bunch of information, moves accordingly. Okay, based on that, and he sees sometimes that some sensors, conflict with each other, so he makes the best decision possible. That's he's driving. The the other person sitting next to him, kind of keeps tab of all these things that are happening, and then looks at it from the perspective of, okay, you know what? Based on this, this, and this, something's wrong here. Something is going wrong from a cybersecurity perspective. We might from a security perspective that we are having, that there's something going on. We might be in the middle of an attack, or we might have some. There are some issues that a compromise might be in the works, or we might even be compromised based on the information I am seeing. So that is that AI security brain, a separate set of AI-based algorithms that are focused solely on the security aspect of the car, not the driving aspect of the car. So as we move towards this futuristic world, this split is what we see right now happening in the industry, and focus is there basically, where you could see them as two different layers, but they're all, abstractly and logically you can see them as two different entities, one working to drive safely, the other one working to see whether to make sure that compromises from a security perspective have not occurred to basically cause damage, right? So with that, from a future, what we see with regards to this and where we go in terms of the machine learning models, the AI models and so forth that can be used here, we see multimodal machine learning. So what is multimodal machine learning? Multimodal machine learning aims to build models that can process and relate information from multiple modalities. So fusing data from multiple sensors and doing prediction on it. So a use case here would be like I stated before, data manipulation, detection, and slandering attacks, right? Slandering attack detection by fusing data from neighboring vehicles and internal sensors. This is what multimodal machine learning that can be used by the AI security brain to be applied. Then we have neurosymbolic AI. So just a quick explanation on neurosymbolic AI. It's basically a combining of neural networks with symbolic approaches. So symbolic AI is basically highly explainable in the sense that it's basically highly explainable as it is expressed as facts and rules. So you have certain facts and rules from a symbolic AI perspective. But the problem is that it lacks coverage. For instance, hard to express entire world knowledges in ontologies, right? How do you, and sometimes you have to represent a face or complex shapes, facts, and rules. So that's where symbolic AI kind of lacks. And also there's not much generalizable methods, and extrapolation is also hard because the symbols are basically localized. Okay. Then you have neural networks, as most of you already know. They're more generalizable. Example, transfer learning approaches, because semantic similarity of objects and so forth, they could translate to say vector similarity with in representations and so forth, right? So the neurosymbolic models, you combine the best from both neural networks and symbolic AI, so that the models are explainable and also generalizable, right? So then they can be extrapolated to harder problems. You can have distributed representation of terminal symbols, fact symbols, and so forth. And there, you can also apply them to more robust cases where the knowledge base is kind of incomplete, right? So what we would use here is, I talked about ontologies before. In this kind of an environment, especially, and with the advances being made in AI, neurosymbolic AI for learning distributed representations of cyber ontologies and inferring facts which are not covered by a knowledge base would greatly help in the AI security space. And then, of course, split learning, pretty much the physical splitting up of learning as the amount of data and all that increases, and you need speed and so forth, right? Training the model both on prem and on the edge would help. Would not only would it help greatly, but it is required. So this is what we see in terms of in terms of the future of AI and the future in terms of infrastructure and so forth in the automotive security industry, in the automotive security space. And that's it for me. Sorry, I was not seeing questions as I was going on, but okay.
No problem. Janahan, thank you so much for the talk today.
Yep.
Really interesting stuff. You have two questions here. I'll go ahead and ask you the first one here.
Yeah.
Um, the neurosymbolic AI concept paradigm is typically seen applied to scene understanding for autonomous vehicles. Intuitively, it would seem that this should also be useful for enhancing security. Do you have any views on this, or if this would even help?
Oh yeah, no, and that's exactly what I said. So what I put at the bottom in terms of the AI algorithms, they were all, I was only talking about from an AI security perspective. So neurosymbolic AI, definitely that was my whole concept there of basically applying neurosymbolic AI from an enhancing the security perspective. 100%. Sorry if I didn't come. I'm sorry if that didn't come across before.
No, I think that's great. Thank you very much. One more question, and this is actually coming from myself. So I have to be honest, I'm not an AI expert or know the methods or anything behind it. But is AI really needed for security in automotive? Like, what benefit are we going to get? Because the vehicles themselves are pretty well defined and the expected behavior is mostly understood. Why couldn't rule based algorithms be employed to achieve the same or better security in vehicles?
Right. So, and this falls behind the entire concept of the AI driver and AI security, the concept that I spoke over there. Using rules and all that, you could go only so far. With the changing threat, with the increase in the kind of the surface, the widening of the surface attack, and the way that in security, especially cybersecurity now, because cars are pretty much becoming moving computers. Like the entire what I spoke about is basically an entire enterprise network with data moving left and right. There are numerous ways that attacks can occur, but they would always occur in a staged fashion. That's the way attacks and compromises mostly occur. The most sophisticated occur, right? Rules and so this basic rules and so forth will not be able to catch that stuff, which is why we use that even in other industries today. Telcos, IoTs, finance industries across the board, cloud, all that. They are basically using AI because because rules, static rules especially, they can only see so much. There has to be a behavioral aspect of that to basically predict what's going to happen. Prediction is the end goal of AI and cybersecurity fusion together, because we should be able to predict an attack before it happens so that we could cut it off at the pass. Because once it happens and then you detect it, it's not as great.
Yep. Okay, great. And just one last question here. You mentioned about where it's going, where the future of AI in automotive is going. And what challenges do we have to get there? And my other question is then, how long is it going to take to get to that point?
Right. So, sorry, that you're done, right? I'll
Yes,
answer.
sir.
Yeah. So, do realize, and one of the things that we have noticed, and I've been in a number of industries, especially telco communications and cybersecurity, for quite some time. The biggest challenges that we face is one of the biggest challenges we face. There are a number of smaller challenges: connectivity, the application of AI, and so forth. The application of AI and so forth, but what we can see today, the futuristic view, is only as good as what we know today in terms of our tools and our current view of technology. What can happen is there could be disruptions in technology that could change our entire base infra view. So even the previous slide where, or you can see in this slide where I showed you the connected future city and where we want to get, there could be disruptions in technology that basically change that view. There could be, and when I say disruptions, I mean disruptions in a good way. There might be a sudden change that basically flips that on its head, and then AI, of course, has to adapt to it. Now, at the same time, there could be changes in AI, and also there could be changes in AI that are pioneered by bad actors. So basically, AI used to attack as opposed to AI used to protect. These we're seeing across the board. We're seeing small, views of these across other industries too. Definitely will apply to something like the automotive industry because it's as you can see, it's quite varied and heterogeneous, right? Those are what I see as the biggest challenges. This is a view we have. This is the way we're going. You have bad actors and threat actors coming in on one place. You have the threat vectors and surfaces increasing. You have technology that's changing at a rapid pace that can flip everything on its head tomorrow with a certain technology that comes up. So all those, the way we see where we are today is what we can present at this point in time. But at the pace technology is going, but 2 years from now, I might have a completely different view.
Well, yeah, of course. Tomorrow everything is different.
Yeah.
One last question, and then we're gonna have to get ready for the next speaking opportunity. Here is Mike is asking about how is fidelity established between external data generators, roadside units, CV2X, other vehicles, and so on, and the AI processors of the vehicle itself. If I have this other thing sending data to my vehicle, how do I know that it's not poisoned data?
No, and that's one. So that is one of the issues where you have to use That's why we have the AI security brain. Now, people can basically talk about encryption and so forth. Why? But that's all the data in transit. Once it reaches the endpoint, if it was sourced by a compromised vehicle in a wrong way, then definitely you're going to get it in a wrong way. So in your vehicle, and this is where when the external data generators, when they send you information, the advantage here that you have in this futuristic view is you're getting information from a number of external data generators, roadside units, other cars, and so forth. The more, the better. If you get information, one of the ways to kind of feel out that some of it is poison data is by comparing it against the others and going, well, he's saying this, but this is saying this, and it's talking about the same thing. So something must be off. There must be something. You could be purposely poisoned, or it could be a default. It could be a degraded piece of equipment that's basically giving the poison, right? And actually, this occurs today even in normal vehicles when sensor fusion occurs. Those and sensor fusion occurs, and this happens a lot. So again, there are methods there, mostly with regards to sensor fusion, but you need a bigger scope now with all the data coming from all places, and that's why you use the AI security kind of methods and so forth to figure out the best possible use, right? And there will be basically notification mechanism, auditing mechanisms that be sent as well, so that if you think that if the AI security brain thinks that a certain piece of data is poison, there'll be notification to basically notify others, this and that. So it's kind of remember, the AI security brain is not just within the vehicle. It's all over the place. It's scattered, right?
All right. Yeah. So, Janahan, everyone, thank you so much for the talk and the interesting topic today. Um, that's going to conclude the third keynote. A round of applause for Janahan, and we're going to get right back into the next really interesting topic with Rawan.
Thank you
So
very
thank you,
much.
Jana.
Thank you. Thank you very much, everyone. Thanks.